Hello and welcome to our final quantum materials workshop of this year, crystal crafts. So you might have seen me before if you've been to some of these other workshops or other events in the department. My name is Helena and I am the Quantum Materials Outreach Officer at the Department of Physics. And today we're going to be learning a little bit about crystals and doing some hopefully fun arts and crafts in the process. So I'm just going to talk a little bit about crystals first. So I feel like crystals, it's the sort of thing that we are all aware of, but probably don't really think about that much. So what makes an object, a material, a crystal? Okay, so there's a fundamental property of materials that makes them a crystal. So to illustrate this, I'm just going to start sharing my screen. So I've got my trusty extra camera here. So there's two objects here. One of them is a crystal and one of them isn't. Which material is the crystal, the one on the left or the one on the right? What do people think? Left a crystal or right a crystal? It's not a trick question. One is a crystal, one isn't a crystal. Even though they're both clear, solid materials, there's something about one that makes it a crystal. Okay, so I think enough people have put in the chat. So I can reveal that the one on the left is a crystal. And this is actually sapphire. So you might know sapphire as being a blue crystal. Well, it actually comes in clear form as well. And I'll talk a little bit about what gives crystals their color in a bit. But this one on the left is the crystal. And this one on the right is simply just some perspex. So it's kind of a plasticky material. And they're both clear and they're both solid and kind of make a noise when you tap, so they're quite hard. But to really understand what makes something a crystal, we have to look inside the material. So we have to look at the atoms inside and how they're arranged. So what makes something a crystal is the fact that the atoms inside of it are arranged in a very structured, ordered pattern. Okay, they can't just be in random places. They're very ordered and very structured. And like I say, in a specific pattern that repeats throughout the entire crystal. Okay, so to illustrate this, I have lots of samples of crystals that I'm going to talk a little bit about today, but we're going to kick off with one in particular that we're working with in the department. Okay, so we grow this in the department, so you can grow and make crystals. I can talk a little bit about that later as well if people are interested. Pop a question in the chat if you want, in the Q&A if you want more information. But to start with, we've got this. So that tiny little black speck there, it's not dirt, it's contained in this container. You can just about see it there. That is a crystal, that's a tiny piece of crystal. And that's something that we call iron selenide. So that's made up of two types of atoms, iron and selenium. Okay, so we've got iron selenide here. And it's really, really small. But if we were to zoom in a bit, it would look something like this. So it's just kind of like a black material. You can kind of see these angular formations growing. That's because of its crystal structure, okay? And if we zoomed in even closer so we could see the individual atoms, it would look something like this. Let me just zoom the camera out. So this is a 3D printed model I have of that iron selenide looking at an atomic level. So we're looking at its individual atoms now. So each of the reddy brown here is iron, and each of the green here is selenium. And so can you see they're arranged in this very ordered pattern. So if I hold it kind of directly to camera, we've got these lines of red and green, and then in the other direction as well, if I flip it, we have red, green. So it's in 3 dimensions. So we have red, green going along the top face. And then we also have green, red going along the side face as well. And this pattern repeats throughout the entire crystal, throughout the entire material, all the way to the edges. And that is what makes this a crystal, this structured repeating pattern. Okay, and we can look at what makes up the smallest repeating pattern inside this crystal. So there's a 3D shape here marked with these little blobs of blue tack here. So it's got 8 atoms here in this 3D parallelogram sort of shape. And this is the smallest repeating pattern. So this shape is kind of copied and repeated throughout the cell. And we call this shape the unit cell. So this unit cell is the smallest repeating pattern that repeats throughout the crystal. And these unit cells can't be any old shape, okay, because they have to fit together and repeat throughout the material. They have to be shapes that tessellate. And what that means is the shapes fit together without any gaps. So if we have a look, I have some little paper shapes. Here's one I made earlier in true Blue Peter fashion of these unit cell shapes. Okay, so if we, let me just get back to the model. So we can see it's this parallelogram shape here. Hopefully you can believe me when I say that. And this is what these shapes look like. And you can see they fit together. So I have quite a few up on my shelf here that I'm just grabbing down. And they fit together with no gaps. I mean, there might be a few gaps here because I made these out of paper and I'm only human, so they're not quite perfect. But they fit together with no gaps in all dimensions. So I can stack them on top of each other in 3D. We can flip them on their sides and they fit together. So in all 3 dimensions, we have this pattern repeating throughout the material. And that's what makes it a crystal. This repeated structure made up of these 3-dimensional unit cells that tessellate, that fit together throughout the whole material. And the unit cell can be a number of different shapes, but they all have to tessellate. Okay, so to illustrate this, we're going to have a think about some other types of crystals. So I'm just going to quickly stop sharing that for a second. So who can think of some types of crystal that, if you want to put some examples in the chat that you can think of that might be crystals? Yeah, good. So sapphire, so I've already mentioned that before. Salt. Salt is a good one, and we're going to come to that first, actually. Snowflakes, excellent. Sugar as well. Sugar is very similar to salt. Diamond, quartz, amethyst is one, yeah. So we're going to come to a lot of these, actually. So this is really great. So I have little samples of quite a few of these, okay, that we're going to talk about. We're going to kick off, like I say, we're talking about salt. So salt is a crystal. And I'm pretty sure we all have that in our kitchen because it's something that I, at least, like to put on my chips. I'm sure a lot of you do as well. So whenever you're eating your chips with salt, you're eating a crystal. And the crystal structure of salt is actually, it's not quite as complicated a shape as this one. It's actually a cube. So if you ever look closely in at salt crystals and you see them, and sugar is very similar as well, and kind of that rock candy, if you've ever seen that rock candy that's like a hard boiled sweet, they're all those cuboid structures. And I've just got a few little PowerPoint slides just to show this. So that was our iron selenide unit cell, if you remember. And if I move to the next slide, this is what salt looks like. If we zoom really, really closely in at the atoms, this is what salt is. So it's sodium chloride is the scientific name for salt. And you can see these atoms are arranged in this repeated pattern with rows in these cubes. And that repeats throughout the crystal. Okay, so another crystal that I saw quite a few people mentioning was diamond. And diamond is actually incredibly similar to salt in terms of its structure. So that's something you might not know. So if we bear this in mind, so we've got our cubic structure of salt, and on the next slide, this is the structure of diamond. So again, it's arranged in this cubic structure made up of cubes, but this time the atoms inside are carbon. So they're all the same atom and they're arranged in a slightly different way inside of that cube. But the cube is still that unit cell. It's still that smallest repeating pattern throughout the crystal. So the crystal structure of salt and diamond is actually incredibly similar. Like I say, diamond is made up of carbon, and you might be aware that things like coal are also made up of carbon, and the graphite in pencil lead also has carbon in it, but that's obviously not diamond. So we've got the same atoms, but it's all about how the material is formed. So diamond is formed under incredibly high pressures and high temperatures that are in the Earth's, just below the Earth's crust. So they're formed within the Earth. And they're the conditions that we need to form diamonds. So it's still carbon atoms, but formed and arranged in a slightly different way. Okay, so they have what's probably the simplest, I would say, crystal structure with those cubes. So we all kind of know what cubes look like. We've had a crystal structure that looks like this. So like I say, it's like a three-dimensional parallelogram here. And there are other crystal shapes, crystal structures as well. So I'm going to go back to my other camera here because I have some more samples for you. So I noticed some people were mentioning this. So I'm just going to zoom down a bit so you can see it. So this is quartz, okay? So it's a clear crystal. And this material, you can see it's very angular, okay? So it has these points, but then these flat sides as well. And quartz has a hexagonal structure. So if we turn it upside down, it's a bit mucky, but you can see we've got 1, 2, 3, 4, 5, 6 sides. So that's our hexagon. And you can see it's in 3 dimensions, and its unit cell is a bit like, I'll zoom out just slightly because that's a bit big. It's a bit like this. So we have that hexagonal shape that kind of grows upwards. And then they often have those points on the top because of how they've been cut. Okay, so that's another type of crystal structure. And this is quartz. And quartz is also made up of 2 different types of atoms. Its scientific name is silicon dioxide. So we have silicon atoms and we have oxygen atoms. And the di part means that for every 1 silicon, we have 2 oxygens. So silicon dioxide, okay? And that's quartz, okay? Some of you also mentioned amethyst. So I have a little amethyst sample here. You can see they're very similar in shape, but the amethyst has this lovely purple color. So it might surprise some of you if I tell you that these are essentially the same material. They are both silicon dioxide, but one has this beautiful color. So what is it that gives crystals their color? Well, it's a combination of 2 things. So both of these crystals are formed within the Earth, and one of the things that gives crystals their unique colors is the natural radiation that occurs within the Earth. So this natural radiation, it comes from 3 particular radioactive elements. So we've got uranium, thorium, and potassium. So they are naturally radioactive, just slightly. So we've always got a little bit of background of radiation going on around us if you were to measure. It's very low, but it's there. And that's what causes these colors, combined with something that we call impurities. So what that means is that within the structure of the atoms, sometimes one of those silicon or oxygen atoms gets replaced by another type of atom. And that's what we mean by an impurity. So in the case of amethyst, we've got that radiation combined with a very small amount of iron impurities. And that's what gives it the purple color. And I have another example here, which is something called smoky quartz. So again, they're all the same material, all silicon dioxide, but with different impurities in these 2 cases. So here we had iron impurities for the amethyst. This one, this smoky quartz, it's aluminium impurities. Both have been exposed to that radiation, but they have different impurities, and that's what gives rise to the different colors. And you can have a look, have a search on the internet for all the other crystals which have colors and see what those impurities are. So different atoms, different elements cause different colors in crystals. So all types of quartz, different colors due to different impurities. So I have some more examples of crystals here. So here's one that if you were at the first quantum materials workshop, you might have come across. So this blue crystal here, which is called copper sulfate. So a lovely blue color, possibly one of my favorite colors. And you can grow this in your school laboratories. There's instructions on the internet about how you can do this. And sometimes you might find that this is an experiment that you do in your science classes. And you can see it's got these sort of angular, I'm not going to pick it up because it can be slightly irritating to your skin. But you can see it's got, again, these angular patterns. And if we look at some smaller crystals to see the individual shapes, here we can see, again, they're sort of these sort of parallelogram shapes. If you can just see. So you can see the sort of outline of the four sides in these smaller crystals. And like I say, if you were at the first workshop, you might remember that copper sulfate is actually magnetic. So it's not a magnet, so it can't pick up paper clips. But in the presence of a strong magnetic field, it's actually magnetic and it gets attracted to a magnet. Okay, so copper sulfate is a crystal that's magnetic. Okay. Just make sure I put the lids on there so they don't fall out. And then I have one final sample that I found yesterday. If you were at the last workshop about monopoles, you might have heard me talking about something called spin ice. So this is what that looks like. This is a spin ice crystal. And so inside this crystal, we can find something that we call emergent magnetic monopoles. So if this is something you're interested in, I'll make sure I let you all know when the videos are on YouTube, but check out the Monopole Hunters workshop and you can find out more information about that. But that's what spin ice looks like. And that's another type of crystal. Okay, so I think I've talked about crystals for long enough. So it's time to get on to the crafting part of our workshop. So the idea behind this is we're going to create our own 3D crystal shapes out of those unit cells. Okay, so like before, I have my my unit cell shapes here. So you've got three options here in that booklet. You can make a cubic shape like salt or diamond. You can make a hexagonal shape like quartz and amethyst, or you can make this, it's called a rhombohedral shape, but it basically means it's kind of a three-dimensional parallelogram rhombus type shape, if you can remember your four-sided shape names from maths. There's a lot of maths in crystals with these repeating structures, so if you didn't know that, there you go. And so you've got your choice of three that you can make, but this works best if you've got a group of you at home or wherever you are, and you all pick the same shape to make, because then you can build your crystal out of these unit shapes and kind of build it up in 3 dimensions. Okay, so let me just get rid of some of those so I have some space. So what you need for this is, hopefully you will all have had a chance to copy out or print out something that might look a bit like this. So this is what we call a net. And what this means is it's a 2-dimensional representation of a 3D shape. So if you've ever had to flat pack boxes, when it's flat and all laid out, that's its net, that's its 2D shape, and then you can tape it all up back into its kind of box shape in 3 dimensions. So that's what we're going to be doing today. So step number 1 is we need to have our net, we need to have our template. So if you don't have that, now's the perfect chance to go and grab that. Next step, we need to cut this out. Okay, so be very careful. Make sure your fingers don't get in the way, and I'll do my best to show that on here as well. So what we want to do is we want to cut out this shape, okay? And we want to be very careful. We don't want to cut off the flaps, okay? We want to cut around the outside of these flaps here because they're very important for sticking it all together. I'm just going to zoom out so I've got a bit more space to work. There we go. So I'm just cutting out this shape. You want to be as careful as you can. And like I say, make sure you cut around the outside of the dotted lines because otherwise you won't be able to stick it all together. Okay. So you want to be careful with this because the more accurate you are and the closer you get to the lines, the better the shape is going to fit together when you're going to try and stick it together. Okay. So if it helps at points to cut off the excess paper like I'm doing, please do. Make sure you gather together all your rubbish so that you can keep things nice and tidy. Otherwise, I'm sure parents and people at home will make you tidy up later. Okay, so we're just cutting out this shape. While we're doing this, I'm going to try and take a look at some of your questions. So hopefully, let's see how well I can multitask. And I can try and answer a few quick ones if there are any questions. Otherwise, we're just going to keep cutting out our shape. If I'm going too slow for you, feel free to cut out more shapes. The more you make, the bigger your crystal that you put together will be. So I've got probably about 6 or so. I can't remember how many I showed you that I've made earlier. So I'm going to be able to add this to my my stack of unit cells to make quite a big crystal now. So that should be quite nice. Okay, so here I have my net cut out. I'm going to get rid of the rubbish for now. Okay, so I'll just start off the next step and then I'll start talking about some of the questions because we've got some really good ones. Okay, so the next step is you want to kind of crease the folds that you're going to make. So the first thing to do is to crease the folds of these tabs, these little flaps on the outside, and we're folding them inwards to create this shape. Okay, so you want to fold them inwards. Okay, so let me have a look at the questions. How do you grow crystals? Yes, I thought that would come up. So this is the perfect time to talk about that. So there are a couple of different ways that crystals can form. So things like diamond and quartz, I've already mentioned, they form naturally within the earth under quite high temperatures and pressures. But you can grow some crystals at home. So what you need to do for that is the exact instructions are on the internet. So if you want step-by-step instructions, I recommend having a little search for that because there are some really fun experiments you can do at home. But the basic idea is you want to dissolve a lot of the material. So let's say you want to grow salt crystals. You want to dissolve a lot of salt in some warm water, kind of as much as the water will take. So it's really what we call saturated. So it's a very saturated solution with the dissolved salt. Okay, so I'll just take a break in the answer and say, so the next step is we want to crease the folds of the sides. So again, we're going to just fold them inwards along the thick lines this time. And then fold them. That wasn't very accurate. Let's try that one again. There we go. So you want to fold these inwards as well and crease them and then just fold them back outwards so we have them creased. Okay, so back to how we grow salt crystals. So if we have our solution with the salt dissolved in water, there's kind of 2 ways you can do this. So the first one, you can simply let the water cool and then evaporate off, and then you get left with salt crystals. Or if you want to create a nice big crystal that you can kind of control the growth of a bit, you want to take a tiny bit of the solution and let that evaporate off. So you get what we call a seed crystal. So that'll be a very small salt crystal. And then you want to put that seed crystal, kind of suspend it on a piece of string and hover it in the center of the other salt and water solution. And then you'll find it might take a few days, but again, as it cools and the water evaporates off, a crystal will start to form around that tiny seed crystal. And then you'll get left with a nice big salt crystal. And that's the same way that you would grow something like copper sulfate, and you can do the same with sugar. So it's all about dissolving it in the water and then letting that evaporate off, and you get left with a big crystal at the end. And the length of time over which you do that can affect how big or how small the crystals are. So if you evaporate it very fast by putting it on a sunny window ledge, you'll have very small crystals. And again, if you cool the water very fast, you'll have small crystals. So the longer you leave it, the larger the crystals you'll get. Okay, so hopefully that's answered quite a big question that a lot of you are thinking. Right, so the next step is we want to glue this all together to form our 3D shape. So first of all, we need to have a think about how this is going to look. So we want it to look something a bit like this when it's fully formed. So what I'm going to do is we want to keep our tabs on the inside to make it nice and neat. So I'm just going to kind of fold it inwards so I can see how it's going to look. Okay, so I can see it's going to do something a bit like that. So this might be a bit fiddly, but that's fine. So that's what it's going to look when it's all stuck together. So if we carefully fold that back out, there we go. So now comes the tricky part, well, the fiddly part, let's say. So what you want to do is you want to glue or tape all the sides together. So I'll show you how you do both. You might find taping it with some sellotape is actually easier, particularly when you get to the last few tabs. So I'll start by showing you how to do it with the glue. And if that gets too tricky, just place some tape over the outside to join the edges together. Okay, so what you want to do with your glue is you want to glue the outside of the flap, and then you want to bring the corresponding face over to it and kind of hold it in place there until it sticks. So you just want to press it down for a couple of seconds. Okay, and you want to do this with the rest of the flaps. So like I say, if that's a bit tricky, feel free to use some tape. You can see I've used tape on some of these ones, and it actually holds it quite a bit better than the glue does. So there we go. So I'm just going to continue gluing and sticking these flaps together, and I'll get to another question. Let's have a look. Right, so there's quite a few people wanting to know where you can find your own crystals. So you can buy crystals. So the quartz and the amethyst are things that I've had in my house for years. And I just got them from a little kind of gift shop. So a lot of gift shops sell crystal, just small bits of crystals, just like this one, just like my quartz or my amethyst, because they make very nice presents and ornaments, and you can often find that they're carved into shapes, and we often use them for jewelry. So I've had in the past some rings and some necklaces that have amethyst in them, and they're quite cheap actually, because they're quite easy to find. I think they're not as rare as something as say like diamond is. So you can find them in gift shops. Other crystals, because they're formed in the earth, below the earth's crust, kind of in the mantle, you're going to want to go to places on the earth where we have access to that mantle. So a lot of volcanic places where you've got a lot of volcanic activity, you can find a lot of these crystals, because they form just under the Earth's surface, and there we have easy access in a way to the area where these crystals are formed. So what I'm doing now is I'm just cutting a few pieces of tape to stick the last base down, because it gets a bit tricky with the glue. Okay, so I'm just going to hold this flap down, and I'm going to stick some sellotape. So they don't need to be too long, they can be just about the length of one of these edges. And I'm just going to tape it down like so. You have to be quite delicate, because you want to make sure it's stuck, but you also don't want to crush the shape here. So take your time and be quite gentle with it, is what I'll say. In terms of other crystals, you can find people selling them on the internet. So the copper sulfate, some of them can be grown in labs, and so they can be made available for sale commercially from there. But yeah, if you just want a simple little bit of crystal, like my quartz, just a little gift shop. You might even find it cut into a nice shape of a cat or a dolphin or something like that as well. Okay, so there we have our fully formed unit cell. And what you can do is you can make even more of these in the same shape, and you can add them to your pile. And like I say, as I showed you before with this, just move the glue out of the way, they all fit together in 3 dimensions. Got a few more. So you can build up your crystal. So the more you make, the bigger your group crystal can be. Okay, and so that's, like I say, the basis of crystal structure. So within these 3D shapes, you have atoms at different places. So they might be at each corner, they might be kind of in the center. But this is the basic premise for a crystal structure. So you've kind of built a crystal structure just out of 3D paper shapes. So I think that's quite cool. And that kind of gives you an understanding of what goes on inside of crystals. You can keep doing this, and you've got the instruction booklet with the templates, so you can carry on doing this over the holidays if you felt like it, for a little bit of more crafts. But what I'm going to do now is I'm going to move on to the next activity that I've got, which is more crafts, but this time focusing on a crystal that I'm sure you'll all have seen, or at least heard of, and that is a snowflake. So you may already know, but snowflakes are a type of crystal, and we often call them a snow crystal for their singular form. And then what we call snowflakes is often a collection of snow crystals. Okay, and what we're going to do is we're going to make some lovely little paper snowflakes. So you might have already done this, so you might know how to do this, but hopefully you'll learn something new about them, because I can tell you a little bit more about the science of snowflakes as we go. So for this, it's hard to see over the white, so I'm just going to put a piece of coloured paper down so you can see my snowflake. So you might have made these before, but we're going to make them in what I like to think is a kind of scientifically accurate way as far as possible this time. The thing about snowflakes is they come in lots of different shapes, but they all have a very similar symmetry about them. So you might have done symmetry in maths at school. So something like it, so they have symmetry like mirror symmetry. So if you put a mirror along this vertical line and you looked in the mirror, it would look the same. Okay. And they also have something that we call rotational symmetry. So, I mean, this is a handmade example, so it's not perfect, but it gives you an idea. If we were to rotate the snowflake, so a different one of its arms were at the top, it looks the same. So we have this rotational symmetry. And it has what we call six-fold symmetry. So we can rotate it through 6 times, because it's got these 6 arms, and it looks the same each time. And the same with if we put a mirror along any of these lines, and also in between the arms as well, we'd find that it looks the same. And so we can do that 6 times. And that's because, again, of its crystal structure. And the crystal structure of a snowflake is also based around this hexagonal shape. So you can see with the 6 arms, you could kind of draw a hexagon in the center there. Okay, so we're going to make our slightly scientifically accurate paper snowflakes. So we're going to make sure they have this 6-fold symmetry, these 6 arms. And I keep calling them arms, but these arms actually have a special name. They're called dendrites. Okay, but I keep calling them arms because that will probably be make a lot more sense. And so they come in different shapes, and they can look slightly differently. So they can have quite a lot of these kind of sticky out bits, these fronds on them. They can have quite hexagonal shapes within these arms as well, but it's all based around these hexagons and this 6-fold symmetry. Okay, so what we're going to want to do for this is we'll need to take some white paper. So I've got some white paper here, I'll just move that out of the way. And you're going to want to draw a circle. So I promise I've got some paper here. I'm going to try not to draw on my table. So to do this, I'm going to draw around a mug. So you might want a mug or a bowl. It wants to be reasonably big because this is going to get a little bit fiddly. And what you want to do is you want to draw around the outside of your mug or bowl, or even, ooh, that just moved. I'm going to turn that over and do that again. Try and hold it still, unlike what I just did. So I'm going to draw around my mug so I have a circle. Okay, and then the next step is to cut out the circle. So you want to, again, be as careful as possible because the closer you can get to a perfect circle, the easier it's going to be to fold it in half, which is what we're going to do, and then into thirds, so we can get that nice symmetry there. So I'm concentrating on making sure. I find circles very hard to cut out. I don't know about all of you, but circles are something I find quite tricky. Okay, so again, I'll put it on the background so you can see it. Now we have our circle. And what you want to do is you want to fold it in half. Ignore my pencil markings on the back. Yeah, that's fine. So you want to fold it carefully in half. And then to get this, this six-fold symmetry and to create those 6 arms, what we then want to do is we want to fold it into thirds. Okay, so this might get a little bit difficult. So we want to fold it into 3. So what I tend to do is I tend to keep the folds quite loose until I know there. If you look kind of there, you can see if I flatten it now, it's going to be in 3. So again, you want to try and make this as accurate as possible so we can get that symmetry. So this is going to be a little bit off because I've not quite got a sharp point there. But I can see that the edges are aligned, which is important. Okay, and so what you want to do next is you could cut out a pattern freehand, but what I'm going to do is I'm going to draw my pattern, just so I know what I'm following. Okay, so as you can see from this example, I'm going to make holes in the middle like this. So to do that, you want to cut a little hole. It can be straight across or it can be kind of in a little diamond shape at the center. And then to create these arms, what you're going to do is you're going to essentially kind of cut out most of this bit here in a V. Okay, but we want to have these little bits. Oh, can't see that. These little bits on here. Okay, and these little sticky out bits. So what I'm going to do is I'm going to draw a design. Let's see. So I'm going to go straight down, and I'm going to have a bit that comes up like this. And I'm going to go down again. I think I'm going to keep this a bit simple. You can have more little bits that come off like this, but I'm going to keep mine a bit simple. And then I'm going to go up in the center like this. And then I want it to be symmetrical. You don't have to make it symmetrical, but I'm going to make mine symmetrical. Okay, so then you want to go back up the other side. And like I say, you want to make this symmetrical. So I'm going to draw my little bit that goes up here and then up like that. And then you might want to put some little cuts along the side as well. So I've got some little triangle cuts that I'm going to make there. So this is where it gets a little bit fiddly. Okay, so you need to be very careful with your fingers on this because we've got folded paper, so it's quite thick. So be careful with your scissors now. I'm just going to move that up again so I've got a bit more space to work. And so what you're going to want to do now is you're going to want to cut out along your lines. So it's very important that you don't make a cut across the edge. Otherwise it's going to, cut that arm off the snowflake. So what you want to do is you want to carefully, I start with the middle piece, you don't have to, but I tend to. So you want to cut that and get rid of the little bit, okay. And then I'm going to just make some little cuts at the side. Okay, so as I'm cutting this out, I can get to another question. Ooh, there's a good question here. Why are crystals so hard? So there's no solid answer. That was a pun. There's no one answer to that, but it's all to do with how the atoms are arranged inside. So again, going back to that crystal structure, they have that repeating structure. But if you remember when I showed you the pictures on the slides of the salt and the diamond, if you saw, salt had quite an open structure of the atoms inside. So it had ones at each corner and then kind of one in the center and then a few more kind of along the edges of the square. Whereas if you look at diamond, it had a lot of carbon atoms scattered inside of that cube. So it's all to do with how those atoms are structured inside that unit cell, because diamond, fun fact, is actually the hardest naturally found material in the world. So you can use diamond, you often have diamond tipped instruments if you're trying to make marks on things like steel or other hard metals, because diamond is actually the hardest, which also means the strongest naturally found material in the world. And it's all to do with how those atoms are arranged. So there's a lot of study that goes into figuring out how to actually arrange those atoms. So that's actually an area of research, is crystal making and growing in order to have the desired properties that you want. So if you want a particularly strong crystal, you need to understand where the best place to put those atoms is. So that's actually a good area of research. Okay. So now I have my crystal cut out, my snowflake. Let's see what's going to happen when I unfold this. I think it's going to be a little bit imperfect, but that's fine. It's homemade. Okay, so we fold out our snowflake. Ooh, you can see I got very close to cutting through that arm there. That could have been a disaster. Okay, and then the final fold. So this is why you want to try and fold it as closely as you can. That's going to be a very thin arm there that I'm really trying not to rip off. I think my other example was a bit more successful, but that's fine. Okay, so there we have our little snowflake. So that's a very, very simple snowflake that I've made. The one that I made earlier is a little bit more complex with the extra little sticky out bits on it. But again, slightly wonky, but we still have those 6 arms and that kind of 6-fold symmetry. And what you can do, if you like, is you can make a little hanging ornament out of this. So you can hang these in your windows or on your tree, and you can also decorate it with coloured pens and glitter. So I'm just going to show you how you can make it into a hanging ornament. So you want to find one of the arms that's a bit thicker, because we're going to try and make a hole in it. And to do this, you want to have a blob of blue tack, and if you put the arm over the top where you want to make the hole, and then you want to take a sharp pencil, and you want to carefully poke that pencil through the paper onto the blue tack to make a hole. So the blue tack really helps here, okay? And then we can just go ahead and poke that through a little bit to make it slightly bigger. And then you can take some ribbon or some string or some thread. So I've got some black thread here, which I'm just going to cut a piece of. There we go. And then a bit like threading a sewing needle, although a bit of a bigger hole, you're going to want to just push that through the hole and loop it back up. And then just tie it together in a simple knot. So to do that, I take both together and then tie it in a knot around my finger. Ooh, okay, that's going to be a bit fiddly. So I'll keep trying to tie my knot while I answer a couple of questions. So we had a question. So when I mentioned spin ice, so that's one that's grown artificially in a lab most of the time. So I'm not sure if there's a place that you can find that kind of naturally, but it's one that we do a lot of research on because, like I say, it has some very special magnetic properties inside. And I'm really finding it tricky to tie a knot on camera. Okay, so for something to be a crystal, have the atoms got to tessellate? So there we go, I've finally got my knot. So we've got a little hanging ornament there. Okay, and like I say, you can decorate this with glitter or pens, but be careful, make sure if you're using glitter, do it over a piece of paper so we can tidy up afterwards. Otherwise, I'm sure you'll have a lot of tidying up to do after this session. Okay, cool, so there's our little snowflake. So I'll get back to the questions now. Okay, yes, so I was talking about how the atoms have got to tessellate. So yes, so that's right. So, but not in each individual atom. So the structure that I showed you of the iron selenide in this 3D model is quite a simple one. So there's an atom at each corner. But if you remember going back to the salt, for example, it had, so it was that cube shape. This is where I see if I can draw a cube. So it had atoms at each corner, but it also had atoms kind of in the middle of each line as well, in the middle of each edge, and then also one at the very center. So, and that was what made up the simplest repeating pattern. So it's not that each individual atom necessarily tessellates. That's only in very special cases where you've only got one at each corner or each edge. But it's that this pattern, this kind of group of atoms, tessellates. So I hope that answers that question. How many types of crystals are there? Lots, lots and lots. And we're finding more all the time. So when I was talking about how you can grow them, you can grow them with particular properties that you want in mind. So whether you want them to be able to conduct electricity, to be magnetic, to be very strong, to have a certain shape. So you can create and make crystals in a lab with properties that you want. So I don't know an exact number, but lots and lots, and we can make new ones every day for scientific research. So there's a question here that says, are crystals poisonous? So I'm not sure about poisonous, but certainly when I was mentioning the copper sulfate, so this blue crystal here, I said that I wasn't going to pick it out because it can irritate your skin, and it can be bad if you then, say if you got it on your skin and then you absent-mindedly rubbed your eye with it or put your finger in your mouth for whatever reason. So that it can be an irritant and it can be bad if you were to eat it. I don't know if it's technically classed as poisonous, but you wouldn't want to do it. So yeah, some of them can be a bit irritant and not good if you were to try and eat them. What if the atoms are very slightly out of place? Then it wouldn't be the crystal. That's kind of the key thing here. So you can insert atoms into that structure. So if we go back to this, I like this model. I think it's a very nice model. So if we were to try and put an atom in the center here, that's kind of that's like adding an impurity. So you can do that, but the core of the crystal is still this structure. So if an atom was slightly out of place, it would have to be just that slightly out of place in every single repeated unit cell for it to still be a crystal. But yeah, that's a good question. And how long does it take for a crystal to grow? So that varies. So in the ones that you can do at home, it can just take a couple of days. In the lab, it might take a bit longer. If we're going to try and be really careful about how it grows, it could take weeks. And then the formation of rocks in the earth can be years and years. I don't know exact numbers, but I'm sure it can take an incredibly long time for something like diamond to form in the earth. Can you change the color of a crystal? Yes, you can. If you remember when I said to go from the clear quartz to something like amethyst, it's not just the impurities, but it's also radiation. So you can expose it to radiation to get it to change color. And you can also manually add those impurities as you're growing it. So I can see someone has talked about how snowflakes are formed. Yeah, and so how crystals are formed has a big impact on what they actually look like. So I mentioned before, when you're making your own crystal and you cool it fast, it's going to have smaller crystal structures, and if you let it grow for longer, it's going to have larger crystal structures. And it's similar with snow in the atmosphere, but it's a lot more variable and a lot more unpredictable. But that's why you get so much variation. And the way that snowflakes grow is, by and large, they require a particle. Like, it's actually how raindrops form as well. To get the rain droplet, they need something to kind of form onto. And it's the same with snowflakes. So they need a particle, and that can be kind of dust in the atmosphere. So it can be pollution particles. It could be desert sand that's been blown up and carried through the jet stream and through the atmosphere in the winds and the clouds. And that's that nucleation. That's called nucleation. And like a nucleus at the center, like an atom or a cell. And that's how snowflakes form. They need that seed, like the seed crystals when you're making your own, to grow. And then the ice can start forming on top of that kind of little particle in the center. Are any crystals edible? Well, yeah, salt, sugar. Simple answer, yes. So every time you have salt on your chips, you're eating a crystal. What's the most complex crystal? That's a good question, and I'm not sure I would know the answer to that. I imagine if you were to look at some of the research that's going on into making crystals at the moment, I imagine some of them will get very complicated. If you're talking about atomic structure, but if you're talking about kind of complex properties that a crystal can have, so if we go back to our iron selenide, this black crystal, this is actually something that we call a superconductor. So if we cool it down to 9 degrees above absolute zero, so that's, what's that, negative 264 degrees Celsius, it can conduct electricity without losing any current through resistance. And it also can have some very fancy, very special magnetic properties. So some crystals can be superconductors, which is quite complex. So I hope you've all enjoyed this. And yeah, keep making your crystals, keep making your snowflakes. If you want to share any pictures of what you've made, you can find the Department of Physics on social media, and also the Quantum Materials group as well. So if you feel like sharing pictures, we'd love to see them, or email them to me as well. Yeah, it'd be lovely to see what you've all been making. So thank you so much for coming, and I hope you had fun, and I hope you have a lovely Christmas break, everybody. So thank you so much.